Hello guys, so this is Tuesday lecture. Uh, we finished last time, or we introduced last time, the NMOS transistor, and we learned its basic operation. Okay, so here is a recap for what we learned. We saw that it is a four-terminal device. We have a terminal called the gate here, which controls the voltage upon the metal. And we said that this metal is actually not a metal. It was made of metal in the early transistor of that type, but then they fabricated out of another material called polysilicon. And we have another two terminals called the drain and the source. And the source here is a source of electrons when there is a current. And the fourth terminal is called the body or the substrate. And we said that we usually will neglect that terminal. And it's usually, by the way, connected to the source. Okay. We said that when the voltage between the gate and the source is larger than a threshold voltage, this voltage is determined, is a characteristic of each transistor. And at that voltage, electrons from both drain and source n-type sub-regions, these two regions here, will concentrate or will attract to the area under the gate. And this area, although we are in the B substrate, B type, will be converted into to an N-type material. And we said it's what's called strong inversion. Okay, and we said that, or we called this region between the source and the drain, we call it channel. Okay, and if it's an N-type material now, because of the strong inversion, we call it N-channel MOSFET or NMOS. Okay, so if VGS larger than or equal to V threshold, we will have a strong inversion. We will have electrons between the drain and the source. So if we put a voltage difference between the drain and the source, or we can say that VDS is larger than 0, then we will have a current flowing from the drain to the source in that direction. Or in other words, we will have electrons move from the source, and that's why they call it source, to the drain. And of course, the conventional direction of current is opposite to the direction of the electrons. Okay, so this was a quick recap for what we have taken so far. Today, we're gonna explore the characteristics of MOSFETs, NMOS in specific. Okay, and when we say the characteristics, we mean by that the relation between ID and VGS, and the relation between ID and VDS. Just like the BGT transistors, we will have their relation between IC and VBE, and IC and VCE. Okay, same as here. So let's start first by the relation between ID and VGS. What we know so far is that if VGS is larger than or less than, let's say less than first, less than V threshold, no channel between the source and the drain, so no current. We only will have current if VGS is larger than or equal to V threshold. And of course, at VDS larger than 0 at that time. Okay, so basically the relation will be let me draw it for you. Here is ID, here is VGS. The relation is found to be that ID equal to, it's two relations. First, because of this, two characteristics. If VGS less than V threshold, ID is just 0. And when VGS is larger than or equal to V threshold, it will be equal to mu n COX W over L VGS minus V threshold square. Okay. We will not, cover how we derive this equation. It's not that hard. Okay. But we need to know or to make sense of it. So first, mu n is the mobility of the electrons, because it's in the NMOS now, in the channel. And it's obvious, if mu n is increasing, that means the electrons are more responsive to an applied electric field. Remember from, our first, month here in that course, when we apply an electric field or voltage difference between a material, we will have electric field, and this electric field will force an electron to move with certain velocity. And based on the material, the velocity may vary. The higher the velocity, the higher the current. So a higher velocity means, or a higher mobility means a higher velocity, so a higher current. So that's why ID is increasing if mu n, or it has direct proportionality like what we see here. COX. This is the oxide capacitance. And remember, Q equal to CV. Any capacitor, the electronic or the charge density equal to the capacitance multiplied by the voltage. The voltage here is our VGS, the gate voltage in reference to the source. And the capacitance is the capacitance of this, capacitors that we created between the metal plate or the polysilicon, and the p-type material. The higher the capacitance, the higher, the charge. So the higher the current, of course. That's why, again, we have a direct proportionality. Then, number 3, the width. This is the width of the channel. And if we go back to the previous lecture, let me show you this very quick. Here is the width. And the electrons move in that direction across that width. So the higher the width, the more electrons or charge that will be moving from the source to the drain. So the higher the current. So if you go back here, the more the width, this will increase the cross-section area of the transistor. So I will increase as well. Number 4, L, length of the channel. And here is, an opposite relation. Because again, if we go back here to the previous lecture, here is the length. It is in the direction of the current. So the more we go, the more distance we have, the more the resistance. Remember, R is equal to rho L over A. Okay, so the more the distance or the length, the more the resistance of the channel, the less would be the current. Finally, the more the VGS, if we look here, Q equal to CV. So the more the V, the more the Q. The more the positive voltage on the gate, the more charges that will be attracted from the drain and the source into the channel region between the drain and source. So the more the inversion. So the more the current as well. Okay, as you see here, it's a quadratic relation. Again, it's not linear relation. All transistors are not linear. Okay, so until V threshold, the current is 0. And then it's a quadratic relation or a parabolic relation here, like this. One last observation here. Number 6. Or not number 6. Let's make it. Yeah. So we call you always this, all these are constants. Mu n, Cux, W over L. When you fabricate the transistors, all these will be constants. Okay? So we usually call that constant Kn because it's n type now. So mu n, Cux, W over L. And this constants, it's called transconductance parameter. Transconductance parameter. And it's measured in ampere per volt square. That's why it's a transconductance. It's current over voltage square. Okay. And remember here, if we look at this equation, I, so here I, D equal to Kn VGS minus V threshold square. So this is ampere here, and this is volt square. So we need a constant, that convert between ampere to V square, which is, it should be ampere over V square. So V square will go with V square, so ampere will equal to ampere. Okay. Good. So that's the relation between ID and the VGS. So let's explore now the relation between ID and the VDS. So let's make it on another page. That's fine. So number 2, ID versus VDS. And just like BGT transistors, we also have regions here. You remember, guys, active region, saturation region? We have also here 2 regions. And for these 2 regions, ID will have a different relation with VDS according to the regions that we are working at. Okay, so let's assume that we are increasing from 0 to infinity. And by the way, if VDS is less than 0, there is no current. We know that. So let's assume the following. Number 1, that VDS is less than or let's name it with the regions. That would be much better. So let's have first our first region, which is the linear region. So let's say this. So MOSFETs, transistors, work between 2 regions. In each region, ID has a different relation to VDS. So let's start first by what's called linear region. And why is he call it linear? We will see now, after maybe 2 minutes or something. In linear region, the characteristic of that region is that VDS will be found to be less than VGS minus V threshold. VDS less than VGS minus V threshold. And the ID is equal to, in that region, Kn. We know, guys, Kn is transconductance parameter, mu n Cux W over L. Then VGS minus V threshold square multiplied by VDS minus half VDS square. Again, it's non-linear relation between ID and VDS. So why is they call it linear? They call it linear for the following. When VDS, just note here, when VDS, much smaller than VGS minus V threshold, we can neglect VDS squared. So at that time, have VDS squared, approximately 0. So ID can be neglected, equal to Kn VGS minus V threshold square VDS. Now look at that. At constant VGS, and remember V threshold is always constant, it's a parameter of the transistor, like beta, for example. At constant VGS, ID has a linear relation to VDS. That's why they call it linear, although it's not in the whole region, it's linear, as we will see now. So if we have here, a graph, here is VDS. Here is ID. So in the beginning, let's draw it. In the beginning, it's linear. Then afterwards, it will bend. And this curve, has a maximum. It's a quadratic relation again. And the maximum will happen at VDS equal to VGS minus V threshold. And you can prove this easily. You can differentiate ID, in response to VDS, partial ID by partial VDS, and equate this to 0. Then you will find the value of VDS that will make ID maximum, and you will find it equal to VGS minus V threshold. So this is the linear region. In the beginning, it's approximately linear. Then it bends a little bit if we increase VDS until we reach a maximum value of ID at VDS equal to VGS minus V threshold. Now, what's going to happen after this? When VDS exceeds VGS minus V threshold. And remember, we now in the linear region, and we said that VDS is less than VGS minus V threshold. Now, what is the other part? The other part is actually another region called saturation region. So number 2, saturation region. And please do not, mix stuff, because saturation region in BGT is actually the first region, this one, which is linear here. Okay. And the number 2, which is active here, it's called the saturation. So don't mix between them. Okay. So basically, in saturation region, we have the opposite. We have VDS larger than or equal VGS minus V threshold. And again, at VDS equal to VGS minus V threshold, this is, the edge of saturation, or the end of the linear. It's a point that belongs to both worlds, both regions. In that region, the saturation region, it's found that ID equal to, it's found that ID is not dependent on VDS anymore. So ID is equal to, let's say, constant or independent of VDS. And the value will be Kn half Kn VGS minus V threshold square, which actually is a maximum value here. Remember, when VDS equal to VGS minus V threshold, if you compensate here, you will get that value. That means when we increase VDS from 0 until the edge, okay, it will continue with the value that it reaches at the edge, which is the maximum value. Okay. But remember, when we take also study VGT, we have, you know, multiple curves here in the characteristics between ID and VDS, or at that time IC and VCE. Yes, and we have that here also. So if we decrease a little bit VGS, we will have another curve that also start. So let me do that. That also start linear, then bend a little bit. Then at some point it just become constant. If we increase it a little bit, again until some point and continue constant. Then that guy that we will draw, then another one here. And again continue constant, and so on. And again, as we increase, the steps are increasing, because the relation between ID and VGS is not linear, it's quadratic. You know, so if we call this VGS1, VGS2, VGS3, VGS4, so basically VGS1 is less than VGS2, less than VGS3, less than VGS4. And the edge is not like VCE saturation in BGT. In BGT, the edge is always, we assume always it's 0.2, because it's really very small. So we can assume it 0.1 or 0.2. Here it's not. Here, VDS set is different. VDS set is dependent on VGS. So you have VDS set 4. You have here VDS set 3. You have here VDS set 2. You have here VDS set 1. And as we increase VGS, the value at which saturation happen will increase. It's not constant like BGT transistor, always 0.2 or something close to 0.2. No. And again, of course, such behavior has a proof, you know. But we will not cover this proof here, because, you know, we're more interested in circuits and how we solve and analyze it, or design it. But again, it's easy, and it's in Cedra's book, Idle Cedra's book. Okay, if you are interested. Good. Final remark here about the linear region. So one application, you know, that is really you can deduce by yourself here from the linear region is how to use this transistor as a variable resistor, voltage controlled resistor. So the use, let's write this, the use in linear, let's do it in another color. So note here, MOSFET can be used as a voltage controlled resistance. How is that? So in linear region, when VDS is much smaller than VGS minus V threshold, we can write ID as you know, have Kn or K, I'm sorry, Kn VGS minus V threshold multiplied by VDS. We can write it that way. So if we divide ID over VDS, of course, this is, you know, the opposite of a resistance. So this is 1 over R. And let's call it RDS, the resistance between the drain and the source. So this will be equal to, I'm sorry, Kn VGS minus V threshold, or R ds equal to 1 over Kn VGS minus V threshold. So at a constant VDS, the change in VGS controls RDS. So it's voltage controlled, you know, resistance. And based on that, we can say that we can use it as a switch. So MOSFET, in that case, can be used as an electronic switch. So your manual switch at home, you just press to light on, light off, on or off. This is by a voltage, okay? So if you want RDS equal to 0 or short circuit, or switch closed, we can say, what you're gonna do? Both VGS, you know, very big, much larger than V threshold. If you want RDS equal to infinity or open circuit, or a switch is open, both VGS less than or equal or even equal to V threshold. Okay. Of course, if it's less than, you cannot compensate in that relation, because this relation is assumed that VGS is higher than or greater than or equal to V threshold. But physically, if you put a voltage less than V threshold, that's, you know, valid. You know, we don't have the relation, but we know the current will be 0. Good. Now let's apply all that, you know, information, characteristics, you know, equations in DC circuits. Okay, that will be used later as we say, biasing for amplifiers, for example. So let's have examples now. Let's go to another first example. So consider an NMOS transistor fabricated with a length equal to 0.18 micrometer. So the length of the channel is 0.18 micrometer, and the width is 2 micrometers. When we fabricated, COX was 8.6 femtofarad per micrometer square. Mu n, the mobility, was 450 centimeter square volt second, and V threshold was 0.5 volt. The threshold voltage of the transistor of the MOSFET was 0.5 volt. Find VGS and VDS that result in MOSFET operating at the edge of the saturation with ID equal to 100 microamperes. So let's solve A first. So ID is equal to 100 microampere, and we are working at the edge of saturation. which means that VDS equal to VGS minus V threshold. Okay, so ID equal to half Kn VGS minus V threshold square. Kn is equal to mu n Cox W over L. And be careful here because some of the constants are in micrometers and some of them are in centimeters. Okay, so you either convert all of them to centimeters or convert all of them to meters, whatever you do. Okay, but unify all the dimensions, either centimeter or meters. Okay, so if you so we know mu n is 450, Cox is 8.6 femto, and femto is 10 to the power minus 15. W is 2 micro, and L is also known 0.18. So if we just make the compensation here, so it will be 1.6 milliamperes per volt square. This is Kn, and the ID is, so this guy is known 1.6 milliamperes volt square. This guy is known also 100 micrometers, it's 0.1 milliampere. V threshold is also known, it's 0.5. So it's a direct compensation here. So from that, VGS is equal to oh, I'm sorry, this is not it was, this is actually 4.3, not 1.6, 4.3 milliamperes. Okay, so if we do that, VGS is 0.715 volt, and from that we can get, because we know that VDS equal to VGS minus V threshold, so it's 0.51715 minus 0.5, so it is 0.215 volt. This is number A. Good. Number B. If VGS is kept constant, so we have VGS still at 0.715, find VDS that result in ID equal to 50 microamperes. Oh, so at the edge of saturation, the current was 100 microamperes, and now the current is 50. That means the current is decreased. So the current decreased to 50 microamperes. That means that we go into the linear region. So the transistor goes to the linear region. That means VDS reduced. So when we calculate it now, it should be less than how much we get it? It should be less than 0.215. So again here, if we go back to the characteristics, guys. So we were at the edge with 100 micro, then it's reduced to 50. So for example, it was here, then it goes here. That means we are in the linear region. So VDS should decrease. So let's see how. So we know in linear region ID is equal to Kn VGS minus V threshold. VGS 0.715, V threshold is 0.5. VDS, which is unknown, minus half VDS square. ID is known, 50 micron. Kn is also known, we got it 4.3 milli. ampere volt square. VGS is still at its value 715, V threshold 0.5. So the only unknown here is VDS. But remember, this is a quadratic equation. So if you continue in that, you will find this equation will reduce to half VDS square minus 0.215 VDS plus 0.116 equal to 0. This will give you two numbers. The first one, or two solutions. VDS is equal to 0.366 and VDS equal to 0.6061. So which one to choose? Both are positives, okay? And we expect always that VDS is positive. We always assume that ID is flowing from the drain to the source, okay? So VDS must be positive. VGS also must be positive if the transistor is conducting, is on. So which one to choose? We know that we are in the linear region, okay? So VDS should be less than VGS minus V threshold in linear region. And VGS minus V threshold is actually 0.215. So this is basically wrong. This is only the valid solution because this is larger than, this one is larger than VGS minus V threshold. And this one is less than VGS minus V threshold. Or with another, concept, we said that we go to the linear region, VDS should be decreased. It was 0.215. So this is larger than 2.215. So we must take this, which is 0.061. Good. That's a good example, actually. Another example, design the circuit shown so that the transistor operates at ID equal to 0.4 milliampere and VD is equal to half a volt. So VD is equal to half volt. ID is equal to 0.4 milliampere. And V threshold has, oh yeah, so there's a typo here. It's not actually a typo, but this book is used VT, for V threshold. V threshold is equal to 0.7 volt. Mu in COX is 100 microampere volt square. L equal to 1 micrometer, and the weight is 32 micrometer. Good. When it says design, that means find the resistors and the resistors, or if you have a battery also, but mainly the resistors. So RD is unknown and RS is also unknown in that circuit. Okay. We know VD and we know ID. So basically, we know that ID equal to, ID is flowing from that point, to the ground, not to the ground, to the minus VSS or minus 2.5. So it's flowing in that direction. So we can determine it from between that point and that point. So it's equal to 2.5 minus VD over RD. This is equal to 0.4 milliamperes. And VD is known. VD is 0.5. So the only unknown here is RD. So from that, RD will be equal to 5 kilo ohms. Good. Now RS. For RS, we need to know in which region the transistor is working, either linear or saturation. Okay, we know VG. So VG here, this is a gate. The gate is connected to ground. So again, this is the symbol of the transistor. This is the gate, the arrow at the source, and here is the drain. And we usually neglect the fourth terminal, which is the bulk, as I said before. So VG is equal to 0 here. And the VD is equal to 0.5. So we know that if VDS is larger than VGS minus V threshold, we would be working in the saturation region. Is that the case? We have here VD and VG. That's fine, you know. Just subtract VS from here and VS from here. So it's the same stuff. So if you subtract the same stuff, you know. So we have, let's do it in more, you know, detailed way. So VD minus VS, VG minus VS. So now VG is 0. And so let's go back a little bit. So VD is half and the VG is 0. So we know that VD is larger than or greater than VG. Good. Subtract VS from both sides. We didn't do anything. So this is VDS is larger than VGS. If you are, you know, greater than something, then if you subtract something from this guy, you will be more larger. I mean, 5 is larger than 2. So 5 is also larger than 2 minus 1, for example, which is 1, right? So again, we will be larger if subtracts V threshold. Good. So based on that, we are working in the saturation region. So based on that, the transistor is working in saturation region. So we can say that ID equal to half Kn VGS minus V threshold squared V threshold is known. How much it is? It is 0.7. ID is known. It is 0.4 milliamperes. How about Kn? Kn is equal to, let's calculate it. Kn is equal to mu NCOX multiplied by W over L. Mu NCOX is 100. W is 32. And L is 1 micro and 32 micro. So we know it. We know Kn. So the only unknown here is VGS. So from that equation, we can calculate VGS. VGS would be 1.2 volt. And before we go, we should check, you know, we said that we are in saturation, right? So VD is half and VGS is 1.2, okay? So VDS, we need now, we need VS to make it. So just forget about that. Okay, so VGS is 1.2. So if we go here, this is equal to VG minus VS, right? Equal to 1.2. VG is 0. So VS is equal to minus 1.2. So we know now the voltage at that point, minus 1.2. And the ID also equal to VS minus 2.5 over RS. This is equal to 0.4 milliamperes. And VS, we got it minus 1.2, minus would become positive, over RS. RS is unknown. So from that, RS is equal to 3.25 kilo ohms. Okay. Now we just want to check on a site. It's not part of the problem. It's just to check on ourselves. So we need to see that VDS. We know that VDS is larger than VGS minus V threshold, but we will do it now, with the numbers. So VDS is equal to VD minus VS. So VD is how much? 0.5. And VS is minus 1.2. So this is 1.7. Okay. And VGS, we just got it 1.2. VGS minus V threshold is 0.7 because V threshold is half. So let's compare them. VDS, which is 1.7, and here is VGS minus V threshold, which is 0.7. That's of course larger than that. So the saturation assumption that we introduce is correct. It's actually correct without doing that, but just to check on ourselves, on our numbers. Okay. Good. So let's take another example. Example 3 here. This is very simple circuit, but very nice at the same time. Okay. Because for some application, we need to force the transistor to work all the time in linear or saturation. And that's the type of circuit or design that you do for such a thing. So for the circuit shown, find the value of R, this value, this resistance here, that result in VD equal to 0.8. So VD is equal to 0.8 volt here. And V threshold is 0.5 and Kn is 1.6 milliampere volt square. Okay. So the basic step here is to know when you connect the drain to the gate, what will happen to the transistor. So when you connect the drain to the gate, since the drain is connected to the gate, for sure VD equal to VG. And for sure VDS is equal to VGS. What is the relation between VD and VGS minus V threshold? If VDS equal to VGS, so for sure, if we subtract from VGS something, VDS will become less than that stuff. Let's do it in red. VGS is actually VDS, and we subtract something from it. So 2 and 2, if you subtract something from 2, for sure 2 will be less than 2 minus 1, right? So basically, based on that, the transistor is in the linear region all the time. All the time. Just a simple connection between the drain and the source, and the drain and the gate, and you are sure 100% of the time you are in the linear region if you want to. Okay. So since we are in the linear region, we know the equation. We know that ID equal to Kn VGS minus V threshold VDS minus half VDS square. Remember, VDS and VGS are equal, so you can just make all of them VDS on the right hand side or all of them VGS, whatever you want. Okay. And remember, VD is a given in the example. It's equal to 0.8, so this is equal to 0.8 here. So ID and Kn is also known, 1.6. So VDS is 0.8, V threshold is 0.5, 0.8 square, and based on that, oh, I'm sorry. Okay, here's another example in which you connect the drain to the gate. So this is the drain, and it's connected all the time to the gate. And that's an example of the design, that forces your transistor to work all the time in some region, either saturation or linear. And as we see in a moment now, this transistor with this design of the circuit, is working all the time in some region. So let's see how. So it's required here for that example to determine R such that VD is equal to 0.8 volt, and ID is not known, but V threshold is known, 0.5, and the Kn is 1.6 milliampere volt square. Good. So here we see that the drain and the gate are connected. So the drain and the gate are connected. So VD is equal to VG. If you subtract VS from both sides, so VDS basically equal to VGS. Equal to 0.8 in that example. Remember, VS here is 0. Good. We know the region of the operating region if we know the relation between VDS and VGS minus V threshold. We know that VDS is equal to VGS. Okay. So here is VDS and here is VGS. Now they are equal. But how about if we subtract something from VGS, from the right-hand side? What will be the ratio? Is it still equality? No. At that time, VDS will be larger than VGS minus V threshold. So let's give an numerical example. So for example, 2 is equal to 2. But if we subtract 1 from here, then 2 will be larger than 2 minus 1, which is 1. Okay. So all the time, VDS will be larger than VGS minus V threshold in that specific circuit when you connect the drain to the gate. And based on that, the transistor is in saturation region. All the time. And basically, if you are in saturation region, you know the equation ID equal to half Kn VGS minus V threshold. VGS is basically 0.8 because it's equal to VDS. Let's square here. And Kn is 1.6. And V threshold is 0.5. So basically, you can determine ID very easily here. It will be 0.072 milliamperes. And I is flowing in that direction. So ID basically equal to 1.8 minus VD, which is 0.8 over R, 1.8 minus 0.8 over R. So from that, R equal to 13.88 kilo ohms. Very nice. Let's have another example as well. Example 4. That's also a nice example. So again, design the circuit to establish a drain voltage of 0.1. So the voltage at the drain here is 0.1, and again, VS is equal to 0. So VDS is equal to 0.1 as well. So first find RD. That's what's meant by design the circuit. Then what is the effective resistance between drain and the source at this operating point? And VTH or V threshold is equal to 1 volt, and the Kn is equal to 1 milliampere volt squared. Good. So we have two questions. First RD, and then find the effective resistance between the drain and source. So we will consider here, the transistor as a resistance. What is this resistance? Good. So let's take it step by step. So first, let's look at we need to know which operating region we are in. We find that the gate is connected to VDD. So VG is equal to VDD. And here, in these circuits, the upper voltage, the pull-up voltage is called VDD because it's connected usually to the drain. In BGT, it's called VCC because it's usually connected to the collector. Okay? Equal to 5 volt. And the VD is equal to 0.1. VDS equal to 0.1. VGS is equal to 5. So basically, this is less than VGS, and of course less than VGS minus V threshold. And also less than VGS minus V threshold. VGS is 5 and V threshold is 1. So this is 4. And of course, 0.1 is less than 4. And based on that, we are working in the linear region. So ID equal to Kn, which is known, VGS minus V threshold. VGS is not known. Oh, I'm sorry, is known also equal to 5, I'm sorry. VDS, which is also known, 0.1 minus half VDS square. So everything when the right-hand side is known, so we can determine ID, it will be 0.395 milliamperes. Now we can determine RD easily. So RD equal to 5 minus VD over ID. 5 minus VD is 0.1. And ID, we just got it 395 milliamperes. So this will give us 12.4 kilo ohms. That's good. Now it asked you to find the effective resistance between. So for any element, its effective resistance is the voltage, its voltage drop across the current that flows through it. So the effective resistance, the NMOS effective resistance equal to its voltage drop, VDS, over the current that flows through it, which is ID. So VDS is 0.1 and the current is 0.395. So it will be equal to 253 ohms. Very small, of course. Very small resistance. Good. The last example. It's a little bit, more complex, but still easy. Because guys, the new thing here is that we have new equations, but same concepts as BGT transistors, So in that example here, analyze the circuit should determine the voltages at all nodes and the currents as well. So all branches, V threshold 1 volt, Kn is 1 milliampere volt square. So basically it asked you to find the ID. Let's be more specific. ID, VDS, and VGS. Good. Before we continue, let's go back to the structure of the NMOS. The NMOS, you have a capacitance, so the gate, then insulator, then the P-type. And when you have a voltage larger than V threshold, you will have, strong inversions. The region, the channel will be, there will be a channel of N type. And a current can flow. That's good. But how much current flows from the gate into the transistor? So we know always that the current drain from the source to the drain, or the drain to the source, the conventional way. But how about the current that flows from the gate into the transistor, the perpendicular one? Remember, it's a capacitance, right? It's a capacitance. You have insulator there, the oxide. So all the time, the Ig, or the current of the gate, is equal to 0. So the current through the gate, Ig, all the time equal to any MOS transistor, the current through the gate is 0. So basically, these two transistors are series. So RG1, RG2 is in series. So VG1 equal to 10 volt, which is VDD, multiplied by RG1 over RG1 plus RG2. And of course, they are equal, so the voltage will be divided equally. So this is equal to 5 volt. So the voltage here is 5 volt. And let's call this V gate, not VG1 or VRG1. The voltage here is VG. Well, this is VG. Good. So let's make a loop here. What do we have in that loop? We have this voltage, which is VG. We have this voltage, which is ID RS. Remember, ID is flowing through the transistor from VD to 0 to ground. And we have VGS here. Remember, this is VGS. Something like VBE there in BJT transistors. So from that loop, from loop 1, you have VG, which is equal to 5, equal to VGS, which is unknown, plus ID, and RS is 6 kilo ohms. So 5 equal to VGS plus 6 ID. Good. This is an equation in two unknowns. So we need another equation. We need another equation. In this particular circuit, we cannot know in advance which region the transistor is working in. It's different from other circuits. So whatever you do here, you cannot know that. So we go back to what we were doing in BGT. We assume a region, and we look at the numbers. If the numbers, if the number is matches our assumptions, then, or our expectations from that assumption, then the assumption is correct, and we just continue. Otherwise, we just go back and assume another one. We have two options here, two ways. If one way is wrong, then we go to the other way. So usually you assume, like there, you assume active first. Here we assume saturation first. So assume the transistor is in saturation region. And remember, saturation region here is similar to the active region of BGT. Don't mix again, okay? So if we assume so, ID will be equal to half Kn VGS minus V threshold square. Now we have two equations in two unknown, because everything here is unknown as well. In number 2, this is number 1, and this is number 2. So these are two equations and two unknowns, ID and VGS. Good. So if we, you know, combine them together, because these are nonlinear equations again. So from here we know that ID equal to 5/6 minus VGS over 6. So we just get this and put it in that equation here. So we'll get half VGS square minus 0.833 VGS minus 0.333 equal to 0. This is a quadratic equation, it has two roots. The first root is VGS equal to 2, and the second root is VGS equal to minus 33. You know, this guy is just like VBE. You can't have a minus on it. So you can't, if the transistor is on, you can't have VGS minus, you can't have VDS minus. So this is, you know, rejected automatically. So our VGS is just 2. It will be, by the way, 1.999. So just if you calculate it by yourself on a calculator or something, but of course 1.999 is just 2. So we get VGS. So we can calculate ID equal to 0.5 milliamperes. And if you calculate ID, you can calculate VS. So if we look here, so VS is just the voltage across RS. So VS is equal to ID RS. It will be equal to 3 volt. We can calculate also VD. So VD is equal to 10 minus ID RD. So the voltage across RD is that way. So 10 minus ID RD. 10 minus ID RD. So it will be 7 volt. So VGS is 2. And now VDS is 7 minus 3 is 4. And remember, you will check VDS here, 4. VGS here is 2. And 2, we will subtract from it VGS, V threshold, which is 1. This is 1. And basically, VDS is larger than 1. So you are really in saturation region. Okay. So guys, these are 5 examples, you know, that really, you know, covers most of the aspects of DC circuits of NMOS. Next time we will take BMOS, which is like BNB transistors, you know, in BGT again. I make always that analogy, you know, to know that we are in the same space, we are in the same topics, but with different devices. Okay, but there are very, you know, huge similarity we can say between both, at least in the concepts of how to solve a circuit. Okay, so next time we're gonna take BMOS and we're gonna explore, you know, the first amplifier, which was called common source amplifier, which is again like common emitter amplifier in BGTs. Okay, so thank you very much and have a nice day. Bye bye.